This is the solution video for problem set 3, problem 4. And this problem asks us first to complete a timing diagram, as we see down below. And after that, we will then be looking at the delays and trying another circuit and comparing the delays. So, to begin this, I'm just going to basically write the amount of delay in each of these gates as I go through it. So, I will start with here. So this is 1 nanosecond. This takes 2 nanoseconds. This takes 1 nanosecond, 1 nanosecond, and 2. And basically, to kind of go through this and be able to fill this in, what I basically want to do is basically write when one of these inputs changes and the time that it changes after each of the inputs or here, so I can kind of trace the signal as it propagates through the circuit. So, for A, I'm basically going to, there's actually a small mistake with this problem, where basically I didn't specify that these have been 0 for a long time. That should have been specified, so technically it's possible that it's undefined at this point because I don't actually know what happened 4 nanoseconds ago. But if you put 0 or undefined to kind of start this off, both answers would be acceptable. But back to the problem. So, this starts off at time 0 and is 0. And then at 2 nanoseconds becomes 1. And then at 18 nanoseconds becomes 0 again. B does something similar. It's 0 at 0. At 2, it's 1. And at 10, it's 0. And at 18, it's 1. Now, Cn is 0 at 0, and then it's at time 2, it's 1, and 18, it's at 0. So now pretty much I only need to calculate at these times, changes. So 0 at 0 will make this at time 1 be 0, and at time 2 this will be oh no, it's not at 2, but 2 plus 1, so at time 3 this will become 1, and then so this is time 10, so at time 11 this will change to be, okay, so that's going to be 1 and 0, so that's going to be 0. And then at 18 it's going to stay 0, so I actually don't need to update this one after that. Now coming through here, we have A and B coming in at 0. This output will be 0. At time 2, this changes to 1 and 1. So actually this is going to stay at 0 up until time 10, when we will input 1, 0, which is going to make this change at time 12, because 2 nanoseconds after 10, this will change to a 1, and then 18 will stay an XOR of 1. So, that's good. So now I need to update this AND gate here. So we'll update at 0, 2, and 12, and 18. Potentially I'm going to have to put things here 1 nanosecond later. So at 0, how to put this? Oh, sorry, let's just say 2. But since I'm also kind of assuming that this has been 0 for a long time, that would be 0 at 0. So 0 at 0, so at 1 nanosecond, this is 0. And at time 2, take 1 nanosecond for this to get through, but this will still be 0. And then 12, and at 12, we're going to have 1 and 1. So at time 13, 1 nanosecond after 12, we will have a 1. And at 18, we'll have 1 and 0. So at time 19, this will be 0. And so we've got this now. So the inputs are here and here. So at 0, 0, we're going to have 0, as we kind of assumed from here. and then at time 2 it's going to stay at 0, and then starting at time 2 we have an XOR here. So 2 nanoseconds after 2 nanoseconds is 4 nanoseconds. We will output a 1, and then at 12 we have a 1 and a 1. So at 14 this is going to drop down to 0, and then at 18 we have 1 and a 0. So 2 nanoseconds after 18, 20 will update to 1. And then we come back up to here. These both are 0 at 1, so 1 nanosecond later. Well, we assumed it starts at 0, so 2, it's going to stay at 0, so I actually don't need to write that. And then 3, it changes to 1, so at 4, this updates to 1. Now the next update is at 11, so we have 11 is 0 and 1 is 0, so this stays at time 11 plus 1 is 12, this goes to 0. 11 and 13 is the next update, so this is 0 and 1, so this is going to rise back up at 14 to be 1, and then at 19 this drops down to 0, so at 20 this will be 0. So now I just need to basically translate this down to here. So I've got my C out is 0 at 0 and becomes 1 at 4. I'm going to scribble these in dark enough so hopefully you can see them well. And then it's going to stay 1 until time 12. And it's going to drop down to 0 at time 12. Go across to 14. Go up to 1. And it's going to stay 1 until 20. And then it will drop down at 20 to 0. And that is my C out. And then now I've got 0 at 0, and I will change to 1 at 4 for S. So keep this going. And then we'll go up to 1. And then that will go across to 14, where it'll go to 0. And then this will drop down to 0 at time 14, and then stay at 0 until time 20, when we will switch to 1. And that completes part 1. And so now for part 2, I'll write those solutions off. Actually, we'll write that here. So what is the delay from A to each output? So that's going to take 2 plus 1 plus 1, so that's 4. That's to S. And 2 plus 2 is 4, so 4 nanoseconds to C out. What is the delay from C in to each output? So it's 2 to S and 1, 2 to C out. And so if I was to build a 4-bit ripple adder using this full adder, the input changes at time equals 0. What time is the sum guaranteed? So it's going to be 4, and then for each additional one, so it'll take 2 nanoseconds to get through the second one, 2 to get through the third one, 2 to get through the fourth one, and so that is equal to 10 nanoseconds. And that concludes this part of the video, and then we will move on to part 2.